Good, welcome back everyone. We want to start the next session, and it's my great pleasure to introduce Andrea Maselli to you, who's based at Gran Sasso Science Institute in Italy, and Andrea will talk about dirty black hole binaries as probes of dark matter halos. Please.
Hello. Okay. Thanks a lot for being here, and thanks a lot for inviting me here. It's always a super pleasure to come back to Técnico, and as you see, I'm a strongly supporter of the IST. I pay and I support economically the Institute, so always very nice to be back. And actually, things that I will talk today has been made with, what I call the Portuguese gang, so mostly with Vitor Cardoso, and then other people here, Francisco Duque, where Rodrigo is now in Copenhagen, then Kyriakos in Destunis in Rome, and then my student Enzo Figueiredo. What I want to talk today. So this is a gravitation. Well, this is a talk on source modeling and gravitational wave emissions from a non-vacuum spacetimes. And what we did here in this series of works that I want to present is like basically a new line, or at least a tentative, to provide relativistic descriptions of what would be like the life, the dynamics, and the gravitational wave emission of compact sources in non-vacuum environments, as we would expect from realistic astrophysical environments. Now, there are basically well, a couple of things that I don't know if like convince is the right verb, but basically I want to pass through the meeting. The first one is that there are a particular class of sources that will be particularly useful, and I'll call them golden sources, for gravitational wave people in order to detect and spot deviations from vacuum backgrounds, and in particular to detect properties of the environments as like features of the dark matter. And these binaries are the very asymmetric one, the one which basically harbor a very massive component and a very light one, which are kind of different from the one that we have seen so far in LAG and Virgo. And then, when you spot more or less which are the kind of sources, there is basically the job for the relativist and the gravitational wave guy, basically which tells you, okay, how do we model this system in a purely relativistic framework, and what are the signatures that we expect, and can we detect them through, well, current and future gravitational wave observations. Okay, let me tell you why first asymmetric binaries. So basically, if you spot the catalog of systems that we have observed so far with LIGO and Virgo, you see that in terms of mass ratio, they are particularly vanilla-like, in the sense that, like, if I'm not wrong, the largest mass ratio that we have found is around like 1 to 30, okay? But with both ground and in particular space experiment and targeting especially LISA, the future satellite, we're going to observe, I can look here, we're going to observe very different sources with very small mass ratios, which can be up to 10 to minus 6, 10 to minus 7, okay? Now, there is a striking difference between the system which are nearly symmetrical one and the asymmetrical one, is that in the second case, the dynamical evolution is mostly dictated by their mass ratio, okay? They tend to slow down a lot, okay? And this particular dynamical feature basically is one of the reasons for why these systems are particularly relevant, like for fundamental physics scenarios and problems. So I'm listing here 3 main reasons. The first one is because of these small mass ratios and this dynamical property, they have a very slow spiral, and which tend to accumulate in the observational window of experiments like LISA, hundreds of thousands of cycles, which are an incredibly large amount compared to what we have observed with LIGO and Virgo. And then, because differently from, unlike the sources that we have observed so far, they have a very rich dynamical evolution with eccentric, non-equatorial orbits, they feature resonances. So there is a lot of variability, which in terms is prone in order to push like parameter estimation into the real good inference scenario. And then, because they live, they assemble, they evolve in astrophysical setup, which are extremely rich in terms of signature and scientific astrophysical cases. science cases. Okay, I want to focus on a particular class of asymmetric binaries, the most extreme, which are the extreme mass ratio spirals. So they are basically assembled by a very massive component with masses between 10 to 4 and 10 to 7 solar masses, and well, a light object could be a star, in the most extreme case, or a light black hole, stellar mass black hole, and so such that the mass ratio is really pushed to the extreme between up to 10 to minus 6, okay? So this is a pictorial representation of the potential wells of the two of the system, okay? Now this is LISA, as we expect, and the noise sensitivity curves. These are different sources. These are, for example, supermassive black hole binaries, and here you see spikes, which are like the characteristic strain, well, for different harmonics of extreme mass ratio spirals, okay? And there are two properties that we see here. First, is that they peak in the millihertz regime, okay? So it's something that we only can observe with space-time space observatories like LISA. And then they peak right in the bucket of the LISA sensitivity curve, okay? So these are golden sources for LISA. Okay, why they are such precious in terms of fundamental physics? Let me go back to what I call point 1 and 2 of my physical reasons why these systems are so important. Well, and mostly because of their dynamical richness. So this is a sketch of of a patch of the orbital evolution that we expect from these objects and from these systems, and you see that basically the orbital evolution is extremely complex because, I mean, it's off equatorial, you see eccentricity, and then here is not shown, but I mean, they can experience resonances at some point in the orbital evolution. But the striking fact is that you can observe these systems for, like, let's say 1 year of evolution in LISA, and these systems will basically complete between 10 to 4 and 10 to 5 cycles in the LISA band, okay? Now, as we say, this is a blessing in disguise. Let me start with a bless. Is a bless because basically if you are able to pinpoint all these cycles with very good accuracy, well, you can have a super precise map of the space-time generated by the binary system, and in principle do whatever physics you want to investigate, provided the physics is there, okay? The disguise is that you need super accurate template to do this, okay? And this is, for example, what the self-force program in vacuum GR has dedicated more than 20 years to produce accurate templates that can basically follow this long spiral and not lose any cycles, okay? What we're gonna do is use these systems and model this system, oops, sorry, wrong direction, in order to answer these questions. And in particular, which are the features of the astrophysical environment in which binary systems evolve, okay? And now let me come to the third system, the third reason that I was mentioning before, so the particular astrophysical setup in which asymmetric binaries assemble, okay? We know in general that, I mean, vacuum is in any case an approximation because any astrophysical system evolves in some rich environment which could be filled by any sort of matter content, gas and fields. The density, I mean, is what mostly plays, I mean, the role of how much this is going to affect the dynamical and emission. But basically, the very basic reasons why this thing is true actually puts out two questions that, I mean, it's worth at least to think about. The first one is if we can infer the properties of this environment as we detect signal emitted by the system. And the second, if we are safe with the waveform that have been produced for vacuum scenarios that we have so far. So if systematics, especially for future experiments with loud SNR, will be important or not, okay? And then there are physical reasons, especially for like asymmetric sources, is that we know that massive black holes is parallel evolve in dark matter-rich environment within galaxies. And then there are particular systems like EMRIs, here it should be IMRI, another class of asymmetric binaries, which is intermediate mass ratio spirals, which may assemble, for example, in accretion disks, so again, like dense environment. So all these just tells you that they evolve and they emit the spiral in region, in arena, where the signals emitted could actually be very strongly affected by the surroundings, so turning like a gravitational wave into particle physics laboratories. Okay, so this is probably one of the best things that we can do with gravitational waves. So using them as tool to bridge the gap between different physical scenarios. In this case, between astrophysics and high energy or fast particle physics case. Okay. Now, why Emrys and asymmetric binaries? So as I will tell you later on, well, the calculation for asymmetric binaries with non-vacuum environment is basically virgin. Okay, like real relativistic calculation is probably done by Vitor, me, Francisco, and other for the. I mean, so there's really a lot to do, but we can still learn some lesson from like comparable mass system, and these are, for example, some results that we derived in a paper with Vitor like some time ago. So basically, we took comparable mass system, okay, and we did some analysis for comparable mass system and extrapolated to asymmetric system, and in particular, what we studied is the evolution of this parallel evolution of this system, where together with their vacuum emission, we also had like two different effects, okay? So given by matter around, so gravitational accretion, and you heard this morning by Katie, also gravitational drag, okay? So these two effects modify the emission, okay? They mostly depend, I hope that you can see here, of the average density, okay, of the medium, okay, which, for example, in the case of gravitational drag tends to slow down the binary dynamics here. And so the simple question that we were asking is, given different detectors and different sources, I'll tell you in a second, which is the maximum values of the density compatible with the minimum values of the density of the medium compatible with the vacuum. So which is the minimum vacuum, minimum density that which we can distinguish from the vacuum case, okay? These are some numbers. I mean, for the sake of this talk, the numbers per se, the absolute value is not too much important, but let me tell you that these are like stellar mass sources that falls within LIGO, Virgo, and the Einstein telescope, and then you see here some dots, and in particular the yellow and the purple one are like the intermediate black hole binaries with 10 to 4, 10 to 3 solar masses, like the massive binary black holes with 10 to 6, 10 to 5 solar masses, and then there are these golden candidates here which provide the tightest constraints, which are the very asymmetric binaries, and actually you see like the intermediate mass ratio binaries, and then down here you see the extreme mass ratio spirals. So the lesson that we can learn, even if we don't have a relativistic description of really asymmetric binaries, but the lesson that we can learn from comparable mass system is that as you shift to very low mass ratio, the constraint on these kind of sources start to become better and better. Okay, so this is something that we should look into, into studying. Okay. All right, and how do we model this? As I was telling you, I mean, the landscape of calculation is really virgin, and because, I mean, just modeling this thing in vacuum GR is extremely difficult, and the cell force is at work for 2 decades. And so in general, when you add like new fields, as Katia has shown, and also matter, everything becomes more complex, where you have more equations to solve in general at the practical level, and then you have the couplings between the matter fields and the gravitational sector, which in general render everything a mess, okay? So it's not an easy task. And even if you want to study like the evolution of this system that I'll show you later, basically is work of perturbation theory, you need something to perturb, which is a background, okay? It's very difficult to generate background solution which describe black hole in some matter distribution, and it's also extremely more difficult to describe like a rotating black hole which comply with astrophysical observation embedded with a matter distribution. Okay, so it's a multi-domain, is a problem. Well, it's a problem with a lot of sub-problems. I mean, starting from the background. Okay. All right, and now let me give you like a super brief overview on how we tackle like extreme mass ratio spirals and asymmetric sources in vacuum, and then I'll show you the difference with the work that we have done with Vitor and other people. Okay, since it's very asymmetric, there is a natural way to treat this system in terms of a perturbation scheme, okay, and the natural parameters to use as a perturbation parameter is the mass ratio, of course, okay. So you basically do perturbation around a background, what I call this G alpha beta 0 here, and then you add the perturbation, you put everything inside your Einstein equation source by, in this case, by the light particle. So asymmetric binaries, there is this massive component, and the light particle that in this scheme acts as a perturbation of the background. You cook out everything in the Einstein equation, and you get this guy here. Okay, this is an Einstein equation sourced by the light particle around. Okay, you want to solve these. And I mean, like at the leading order, like depending on whether your background is not rotating or rotating, you get what are called like the Regge-Wheeler or Teokovsky equation, basically. And you want to know this because this gives you the phase evolution of the binary. Okay, you can actually decompose the phase evolution in terms of a power expansion of the mass ratio here. The leading term which will go as 1 over q. Remember, q is the thing which is 10 to minus 5, 10 to minus 6. So this guy here is very big. And then you have like what are called first post-adiabatic and second post-adiabatic term, which need like second order correction in these ansatz here. And the problem is that accuracy requirement for extreme mass ratio spirals will actually demand that we know at least this term here, okay, in order to get, well, a subradiant accuracy in the orbital evolution, which means basically that, well, we need to compute second order correction and all the first post-adiabatic stuff, which is something that people are computing now for Kerr solution in vacuum GR, okay? Okay, the thing that the perturbation is very easy. Basically, you decompose H in polar and axial perturbation. There is a standard way to do this. And the good way is that in general relativity, like the 3 components of axial perturbation and the 7 on polar perturbation can just massage and mixed in a way that the perturbation just reduced to 2 wave equations here. Okay, I'm talking about now non-rotating space-time, but the generalization to Kerr is basically the same, just more involved. You solve this perturbation here, okay, and you want the axial component and the zeta component, because then the axial component and the zeta component tells you the flux or the fluxes emitted by the binary at the infinity at the horizon, and then you need the fluxes because they go into the dynamical equation for the orbital phase and the orbital radius of the binary. This is what we do in GR, in vacuum GR, and this is what we're going to do in non-vacuum GR, so assuming matter, okay? All right, and at this point I can move on. So as I was telling you, the first thing which is crucial is and which is lacking. I want to study perturbation theory, to study asymmetric sources, but I need a background, okay? I need a background which is different from Schwarzschild, which is a relativistic description of a space-time describing a black hole surrounded by matter. And to do this, we actually didn't reinvent the wheel, because actually Einstein did this in 1939, among many other things. And we actually used what is called the Einstein cluster prescription. So basically, this is a super clever way to treat a collection of dust particles around the black hole. And basically, there is a procedure in which you average out, in a sort of mean field approximation, the geodesics of all the particle, and then this collection of dust basically reduce in an effective stress energy tensor here, which has the form of an anisotropic stress energy tensor with the tangential pressure and density of the matter around. Okay. So the game here is that, okay, we have this, which which describes the matter outside the black hole, and we want to find a background solution. So in this case, I mean, we moved from like non-rotating solution, so we ask for a spherically symmetric space-time, okay? And for the first job, for the first paper, we actually assume that the matter distribution describing like the matter outside the black hole was actually reproduced in the Erdquist profile, which is one of the profiles most commonly used to describe like dark matter complying with astrophysical and numerical observations, okay? And numerical simulation, okay? We have actually generalized these to any dark matter profile, but I'll talk to you later, okay? So when you have this, you basically have everything, because I have my line element ansatz, I have the stress energy tensor which sources my Einstein equation, so just I need to do is solve a bunch of differential equation, and actually with this particular choice of the matter, which reproduces like the Erdquist profile, everything turns completely analytically. So basically you can solve the Einstein equation and get in a closed form, well, both the density of the matter, of course, and then the GTT component, and also, well, the M of R, which is the GRR component, okay? And as you see, it's very close by to the Schwarzschild prediction. Time this guy here, which is actually what we called a redshift factor, okay? And so in the, basically, it is proportional in the limit of m over a naught, what we call the compactness of the dark matter halo around the black hole small, which is proportional to this factor here, which really resembles a redshift factor. This is very crucial for the things that I'm going to say. Okay, and then basically we look for asymptotically flat solution, which also have like a black hole horizon at 2m. Okay, so we have our background, and when you have the background, what you can do is basically study, well, the properties of this background and then perturb it. Okay. The first thing that I want to do is study the properties. So what I want to do is study the geodesic structure, and so understand how massless and massive particles behave. And there are two key ingredients in this case that matter, which are like the innermost stable circular orbit, which is the last stable orbits for like massive particle, this guy here, and then there is the light ring, okay, which is the only unstable circular orbit for massless particle, which is this one here, okay? The 3 and the 6M are the prediction from the Schwarzschild case, and then these are actually the corrections that you get because there is the dark matter distribution given by the Ehrenquist profile outside. Okay, and then from these you can basically compute like, well, the physical quantities, which are like the frequencies at the light ring and the frequencies at the ISCO. Okay, the light ring is particularly important because basically it controls the illumination of the black hole. So, for example, the black hole shadow. Okay. All right, and as you see here, there is always like the Schwarzschild prediction on top of this, but at the linear order, like the changes with respect to the Schwarzschild background are pure redshift factor. So basically at the linear order you can reabsorb these, the changes with respect to the vacuum background because of this redshift given by the compactness of the halo. I probably forgot to say that M is the mass of the halo and A naught is the typical scale of the halo. Okay, so like nonlinear correction are the one that really tells you like the presence of the halo, which are given by this guy here. Okay, which is actually expecting, because what you get basically is that these particles, light or massive, are moving in a different potential well where the mass now is dictated by a different components and not only by the black hole one. Okay, so at the leading order, okay, we have like that only the redshift is mostly affecting the dynamics. And then basically if you compute like correction of a putative black hole shadow, this would have like a nonlinear correction of the order of this guy here for realistic M over I naught, so mass and scale distribution which comply with astrophysical observation of dark matter. Okay, all right. We can then ask, I mean, what happens to gravitational wave observation, because, I mean, this is going to probably provide the most striking fact. Well, all of this is because, I mean, there is matter outside, but, I mean, it's really important when you model things that trying to understand whether these things actually pop out really. And because they affect, I mean, the basic question is they affect like the gravitational wave emission and the geodesic motion, but the other question is in which way and how we can disentangle it. And for example, the previous way tells you that it's going to be extremely difficult from geodesic motion to disentangle this because, I mean, there is only the redshift which plays a major role. Okay. Let's see what happens for like perturbations that we need in order to compute the dynamical evolution of asymmetric binaries. Okay. And the methodology is basically the same, but that everything becomes extremely more difficult. We basically took 1 year, I mean, to complete the second work on polar perturbation. And this is because it's true that the metric gets the same decomposition here. So you still have your very nice ansatz here, but then you have other stuff to decompose and to perturb. You have like the fluid velocity and then the density and the pressure components of your fluid. And then all of these, in principle, will have their own dedicated equations to be solved, okay, within the game, possibly coupled all together. Okay, the only, and this is for example the expansion for the tangential pressure. The only good thing is that since we are in spherical symmetry as a background, we can still benefit from a property that axial and polar perturbation decouple as in vacuum GR. So you can treat the two sectors, so the one corresponding to this and to this, well, separately. Okay. Okay, and as we will see, there is also basically another difference is that in vacuum GR, well, through a sort of like basically coordinate transformation, you can always reduce everything. The problem of decomposing like the 3 + 7 equations that you would have in those cases to one for the axial case, one for the polar cases. Okay, this is not always the case when you go beyond vacuum GR, and we're not going to find this again, at least for the polar sector, which makes everything computationally more difficult. All right, so how everything changes? Okay, this is the result for the axial sector. Now, the axial sector actually remains quite similar to the vacuum case, because this is as you see, basically the functional form of the Schrödinger-like equation which determines the evolution of the perturbation R is basically the same, okay? What changes really is, of course, the source term, well, because it contains like the background metric of the black hole, but also the scattering potential here that I'm drawing for different cases, and the blue one, well, hidden a bit, is the Schwarzschild vacuum case, because now the axial scattering potential contains like the new GTT component, which is not Schwarzschild anymore, plus there is the mass function and its derivative here. So it contains information on the matter distribution, okay? And well, these terms will be 0, and this will be constant for pure vacuum Schwarzschild background. Okay, okay, and this is the change in the scattering potential, and well, depending on the compactness of the halo, there are certain parameters. And also, there is an important part, is that axial perturbation don't coupled to fluid perturbations, okay? So you don't see any delta rho, delta p, or delta velocity, okay, because they couple to the polar sector. All right, so how the fluxes change. So this is the relative difference between the matter and the vacuum case, the relative percentage difference, okay? So basically, you take an extreme mass ratio spiral, which means you take a system like 10 to 6 solar mass and 10 solar masses, okay? And the light particle sits at different orbital radii, okay? 10, 7.5, 12, whatever. And then you compute like the energy emitted by this particle. Okay, and this is the L equal 2, M equal 1 mode, okay, for different halo configuration. And this is the relative difference between like the halo, the vacuum and non-vacuum prediction. Okay, it looks a small number, okay, it's like 1%, something like this, okay. But this is a gigantic number in principle for an extreme mass ratio spirals, okay, because basically this is the standard, well, abusing about the term, like instantaneous variation of the flux with respect to the vacuum. But then when you pile up this variation on top of the 10 to 4, 10 to 5 cycles, okay, that the extreme mass ratio spiral is expected to perform until the plunge in 1 year of observation, this difference becomes enormous. Okay, and indeed, well, we basically made a rough calculation, and this difference here for 1 year of observation, which would correspond to 500 radians. Okay, of different, which basically means two things: that if you have the wrong template, you don't see it, okay, or you completely infer the parameters, so you need something more accurate, okay. So in principle, this thing here tells you, oh, well, okay, even just axial perturbation looks that detection of these things from gravitational wave sources are extremely promising. But here comes the redshift again, because if you take a low compactness expansion of basically all quantities that you have in the game for the axial sector. So I systematically expand the scattering potential, then the source term, and even basically my operator here, which dr in dr star, the orthogonal coordinate. Basically, the leading order, my Schrödinger-like equation for the axial component becomes this. And then what you see is that with a suitable redshift redefinition of all the frequencies and the mass scales, so omega, basically mu and capital omega, the geodesic frequency, basically this equation here, there is an equivalence between the vacuum redshifted and the halo axial problem. Okay, so basically the redshift doesn't hit only the geodesic structure, but also the axial component, okay? And with this redefinition of the variable, you are able to turn your, basically to change between the vacuum axial and the matter-dominated problem, okay? And you see this is basically, again, the plot with the relative difference between the fluxes, the axial fluxes generated by this light particle, and the solid line corresponds to the same numerical setup that we've seen before, so just the relative difference between the matter case and the vacuum case, okay? But then I take the vacuum case, I redshift everything according to this procedure, and then I do again the comparison between now the vacuum redshifted and the matter component. And as you see, there is a super strong decrease, okay, in the difference between now the vacuum and the matter case. Basically, what you're seeing here is just a leftover of nonlinear effects, okay, in M over A naught, which tells you that probably the effect will just come out in a redefinition of the frequency and the mass scales, okay, and probably everything else, so this nonlinear component could be, at least for the axial sector, too small in terms of relative differences to be detected even with a super long and super slow spiral as the one provided by extreme mass ratio spirals, okay? So unless something new pops out, axial and geodesic structure, axial fluxes, look really dominated only by the redshift factor and don't look extremely promising in terms of spotting the difference between vacuum and non-vacuum case in the spiral, looking at a pure relativistic description of a black hole surrounded by dark matter. Okay, we have generalized basically this thing to all these results were actually made for this analytic, very nice Ehrenquist profile, but we actually generalized this with my student Enzo to pure basically to any numerical profile with a radial dependence rho. So Enzo basically have written a code which solved the exactly same problem, but without any ad hoc specification for the matter profile, okay? And so basically we have this paper that came out recently in which we extended the results for the geodesic structure and the, another 2 minutes and I'm done, and the axial fluxes to different dark matter profiles. So in particular, we studied the numerical Ehrenquist, but plus we included the Navarro, Frank and White, and this other model, which is called the Enisto model. Okay, and at least for the axial fluxes and for the geodesic structure, what we found is that the result of the story is always the same, because what we found is this is, for example, the relative difference in the light ring, as I showed you before, but now not only for Ehrenquist, but also for the Navarro, Frank and White and the Enisto model, okay? And what we saw basically is that changes with respect to the vacuum for the geodesic frequency, even in these two models, okay, are basically can be interpreted of a redshift scaling, okay. This is this is the relative difference, okay, and this is really what is left over in the difference, 1 minus m over a naught, so the redshift scaling, and you see, and this is the compactness of the halo, and you see that as the compactness decreases, where the slow compactness approximation becomes more and more valid, you see that you get that the redshift scaling becomes more and more accurate. Okay, and here there is, I hope that you can see, there is a zoom on the law on this part here, and also what we saw basically is that with all models there is a sort of universal behavior of m over a naught smaller than 10 to minus 3. Okay, so everything dominated by, for any type of models that we studied, okay, not only the Ehrenquist, everything was scaling as the redshift factor, and we were getting a sort of universal behavior for compactness smaller than this guy here. Okay. Okay, and this is a generalization of the fluxes that I showed you before for different profiles. Okay, and so the Navarro, Frank and White, and basically everything is the same. So if you redshift the fluxes, everything becomes smaller. Okay, I have just 2 slides left, and then I can leave. So where is the juice? Do we have any chance if we really want to model everything in a coherent relativistic wave? Well, the answer is in the polar sector, okay, at least from our first calculations, and this is because of the couplings, okay, because the couplings basically between like the gravitational variables, here these are the tensor perturbation, and the fluid variables, okay, this is the perturbation of velocity and the perturbation of the density, which renders everything more complex, okay. Now you don't have any more like a Zerilli-like equation, but you have to solve like a system of 5 ODE coupled together, sourced, okay, and then you also have more ingredients, because basically you have a pressure perturbation, both the radial and the tangential one, and you have an equation, you need an equation of state to connect them with the density perturbation, which takes into the game also basically the sound speeds of the medium. Okay, now these are the fluxes that you would compute in vacuum, okay, GR, and for like a dark matter halo with the Ehrenquist profile, solving this equation here, you see that there is a decrease in the energy fluxes if you move from vacuum to the non-vacuum case, which it's an hint of the fact that, again, there is a redshift because the wave basically is passing through the matter profile, the potential well of the matter outside the black hole. So the question is this, again, everything dominated only by the redshift factor, or there is something else? Well, there is something else, because this is the usual, basically, plot with the relative difference, but now not of the axial fluxes, but the polar 2-2 mode, which, by the way, in any case is the dominant component in the gravitational wave dynamics of asymmetric binaries. And what you see here is that even if you redshift with the same basically tools that we have seen before, the vacuum fluxes, there is a decrease, but in the majority of cases is not enough to describe basically to put down the differences, which actually remain quite high, and particular configuration can be actually extremely high and possibly hint for a good source of detectability. Okay. Which means that, well, there is a lot of job to do, and in particular that there is good chance that we need to work out, at least to try to work out like realistic waveforms in order to model the system and try to embed like the effects on the gravitational wave emission. Okay, I'll leave with the summary, and thank you so much.
Okay, thank you so much. Other questions for Andrea? Yes. Yeah.
Hi, thank you. Two quick questions. First, is there hope to repeat these calculations with a rotating black hole background? And second, if there is a halo, what is more important? Do you have to take care of the spin of the black hole, or is the halo by itself like does it just swamp the behavior of the spin?
So concerning the spin, I'm trying to work on it. Well, first on a slowly rotating approximation, so like the usual Arthur-Thorne things. The thing that honestly I haven't understood, which really, I mean, the perturbation will be basic. I mean, like in principle, like computing everything should be relatively easy. What I don't know is if the Einstein cluster ansatz will survive to this. Because basically, I don't know if I introduce a non-static space-time is basically the average procedure is actually self-consistent. So what I'm saying is that we are studying, this is what we are studying now. So we are actually trying to extend like that kind of description in order to take into account like a GT phi into the metric, and then see what happens. And the second question I forgot?
What's more important, spin or halo?
For what? What more important for what? Sorry.
I mean, in the modeling, right? Then either thing is going to perturb
in general for this kind of system.
Yeah. So
no. Okay. So I'll tend to say in general, like the spin of the central black hole is extremely important for several reasons. First of all, I mean, I think it's like the parameter, like for example, for extreme mass-rate spinor that you measure with the tightest accuracy. Okay, and it determines a lot of things. I mean, like the shift really, like the spin really shift like the plunges, because I mean, if you have like maximally spinning black hole, you can really go down like close to M, and which changes the SNR, so it will have an important effect even just for. Basically, it could be, for example, that we detect only very fast spinning black hole just because there is a selection bias, in the sense that the high spin will just promote the SNR, only the SNR will be large enough to be above the threshold. So just to tell you that it's going to be super important for the detectability, but also to promote the sources to be actually detectable.
But at least in the calculation that you just could describe that you're starting, you're not going to get there, right? Because you're taking a small.
In the first part, yeah, okay, yeah, in the first part, yeah.
Anyway, thank you.
Yeah, there is one question over there.
Hello? Yeah. Can I?
First, no? Okay. Yeah, please go ahead.
Yeah, so, yeah.
Oh, yeah, sorry.
So in one of the slides, you're talking about the Einstein cluster prescription. So there you had showed the energy momentum tensor to have a zero radial pressure. So is there any qualitative way to explain why is that so? And the next question is, in presence of rotation, will that radial pressure be of same magnitude as the tangential ones?
So the tangential pressure just come out from the average procedure, basically. You get just to resorting. I mean, when you make this average procedure, basically you come out with a prescription for the T mu nu in terms of a summatory of the particle, which provides naturally this tangential component. And the inclusion of the spin, yes, I mean, it may lead like to have a radial. Well, I don't know the answer for this. It may lead like to have an extra component in the stress energy tensor. Yeah.
Thank you.
So just a quick question. I know a lot of people have looked for pulsars at the galactic center, so you can get an extreme mass ratio sort of in spiral in the form of a pulsar around, Sagittarius A star. Is any of this work applicable to that, sort of modeling what differences there might be based on the local environment or the environment of that extreme mass ratio in spiral?
So I'm not super expert on that case, but I think that they were looking for pulsars, because that would probably be like a super definitive golden tool, like for making test of GR, any sort of astrophysical test, because we will have like radio beams and then in the potential well of the massive black hole, so you can do everything. And what I think the difference is that these extreme mass ratio spiral evolve at very close distances. So like we're talking about 10 m, okay, like 20 m's. Like this is, I would expect like a 10 to 6 10 solar masses to evolve in 1 year in the LISA band, starting from less than 10 m of distance, roughly 8, 9 m. I think that the pulsar that we're looking for is way farther.
Do you have a sense of what the complementarity would be between that system and sort of the closer systems that you're looking at? Would it be a different parameter space entirely? Would you be looking at the same sort of?
I think that the very difference is that in that particular case probably will be dominated by the gravity of the dark matter and not the one of the black hole, to be honest.
Okay, thank you.
Okay, thank you very much. We need to move on, so let's give a big applause to our speaker again.